Hi everybody, welcome to lecture 25 for Mechanics of Materials. Specifically today we are going to finish chapter 5 and we are going to be looking at an analytical solution to doing shear moment curves. Now we've already talked about the graphical solutions, so this material applies to that exact same material. This is just an alternative analysis technique. Any shear moment diagram pretty much can be constructed one way or the other. However, some lend themselves to a graphical solution while others lend themselves to an analytic solution. So basically we have a couple of relationships that help us. When we have a distributed load curve, for example, in this particular drawing you'll see that we have a fixed value of 20 kilonewtons per meter applied to the first 6 meters of the beam, and there is no support here at B. That's just the end of the load, but then at the other end at C we have a support. So the last 3 meters are unloaded, but we have a 20 kilonewton per meter load curve, so our W value is equal to 20 kilonewtons per meter. We have two mathematical relationships. The first derivative of shear with respect to x is equal to minus W, or minus the load curve. Now in the instance that we just showed, W is a constant, but in any case, whether it's a constant or it's a function, you can treat this as a first order separable differential equation. Separate dV equals negative W dx, and then integrate both sides. Now we have to be talking about a definite integral, and what we find when we perform this integration then is that the value of shear at one point, at point D, the terminal point in this case, minus the value of shear at the beginning point, is equal to the negative of the area under that load curve between C and D. And continuing with that thought, the first derivative of moment with respect to x is equal to the shear. We can separate that equation, integrate between two fixed points, and we determine this equation that the integral of v dx, or the integral of a shear function dx between those two limits, is equal to the magnitude of the moment at the end of the interval minus the magnitude of the moment at the beginning of that interval. So why are we interested in doing this? Well, the real thing is we're looking for maximums or maximum absolute values of shear and moment, because we want to design for the place on the structural member that bears the most load, or that reacts in the most profound way, because we want to prevent our structural member from failing, and to do that we have to design it so that it's strong enough to everywhere bear those maximum values of shear and moment. So as an example, I drew a beam, a structural member that had a fixed support at A, no support at B, and a rolling support at C. From point A to point B, which was a distance of 6 meters, we have a distributed load in the amount of 20 kilonewtons per meter, and this is not representing a separate point load. That's representing the point load equivalent of that distributed load. So anyway, the first thing we need to do this analysis, as with any analysis like this, is to do a free body diagram. So we first write that since W is consistent, 20 kilonewtons per meter, and it extends for 6 meters, that the equivalent point load W is equal to 20 times 6, or 120 kilonewtons. Now the next thing we need to do with that is to determine how much of it is borne at A and how much is borne at C. Since this load is not distributed in an equal fashion, in other words, it's not halfway between A and C, and the load does not extend across the entire beam, we have to determine the reaction at A and the reaction at C using a summation of moments concept. So we do that. We say the summation of moments about point A equals 0. So we have the equivalent point load, 120 kilonewtons, times its distance from point A, which is 3 meters. And if you look at the diagram again, you'll see that that rotation would be clockwise, meaning it's negative. Then R sub, this says R sub B, but it should say R sub C, times the distance from A to C, which is 9 meters. And that moment, since the reaction at C is pointing upward, that would create a counterclockwise or positive moment, and that those two things will have to equal 0 in order to maintain static equilibrium. So when we solve for that, we find that the reaction at C is equal to 40 kilonewtons, and since we know that the reaction at C plus the reaction at A add to 120, we know that the reaction at A is 80 kilonewtons. So here's a really rough free body diagram with showing those two reactions. Now, I want to next find the shear diagram. I want to draw the shear diagram, but instead of doing it graphically, I want to do it using this equation, this first order separable differential equation. So the first thing is I have a discontinuity here at 6. That's where the load ceases to be applied. So I'm first going to look from 0 to 6 feet on the structural member. So the shear at 6 feet minus the shear at 0 feet is equal to the negative of the integral w dx. W is 20, so I put that in here. I know that my v sub 0 value is 80 because I know that my reaction at A is 80. So I know that immediately, just a smidgen beyond to the right of the support at A, that this shear will be equal to 80 kilonewtons. So that's my v sub 0 value. V sub 6, or the shear at 6 meters, is going to be 80 minus the integral from 6 to 0, from 0 to 6, of 20 dx, which integrates to just 20x. So we come up with the idea of 80 minus 20 times x. Well, the x, where I plug in 0, that would just be 0, so that's 80. That gives me the value here. But the value here is 80 minus 20 times 6, which is 80 minus 120, or negative 40. Now, the other thing that you can see, and the thing that I really want to point out, is because w is a constant, and this function is 80 minus 20 of x, 20 times x, this is a linear function, meaning that v is going to change in a linear manner from 80 kilonewtons at 0 to negative 40 kilonewtons at 6 meters. Now, the next part, from here to here, the last 3 meters, is going to remain at negative 40 because there are no additional forces or reactions beyond that. The other way that you can see it is the reaction here at C would have been 40, and if we had just cut from the right to the left, we would also see that the reaction just one smidgen beyond that support at C would be negative 40. So it's straight line. So the shear diagram looks like a straight line going from 80 kilonewtons down to negative 40 kilonewtons, and then remaining at negative 40 kilonewtons until we get to the end of the beam. All right, so that's just, I just sort of redid it here in a little bit nicer fashion. And so the next thing I want to do is to determine what is the moment. Well, I'm going to use the same idea. I now have a function for v, and I know that here we go. Dm dx is equal to v. So dm dx is equal to that function, 80 minus 20x. So I separate this equation and take the integral of both sides. And the first thing I want to do is I want to look at where that moment is going to be a maximum. Now, this is a little bit of a graphical technique, but when I look at this feature, I want to know where v is equal to 0, because if you look at this equation again, dm dx is equal to v, so that this moment is going to maximize where v is equal to 0. So I wish to find out where v is equal to 0, and I do that just by plugging it into the equation and find out where that value occurs as 0. So in other words, if I go to this equation, 80 minus 20x, and I set it equal to 0, I get AT equals 20x, divide both sides by 20, and I get x is equal to 4. So that means that 4 meters from the start of this diagram, right here, I'm going to have a maximum value of m. And that's really, or maximum or minimum. It says I'm going to have a zero slope on the moment curve at that point. So I want to determine where that occurs and what its value is. That's why I went from 0 to 4. Now then, the other part of it is when you look at the moment curve for the first part of the beam, from 0 to 6, this function is a second order equation, and that makes it a parabola. So I know that it's parabolic until I get to 6 meters, and then from 6 meters to 9 meters, I'm back to a constant b. So that means it's going to be a linear equation, like right here, and my moment is not, the change in moment, the moment curve is going to be linear. So up to 6 feet, it's going to be parabolic, and then it will be linear from 6 feet to 9 feet. Anyway, going back to the first 4 feet, I integrate dm, and I get m at 4 minus m at 0. And I integrate this side equal to 80x minus 20x squared over 2, which of course is just 10x squared. Evaluated from 0 to 4. Plug in my 4's because the zeros go to 0, and I get 160 kilonewton meters. So my maximum moment on this beam occurs at 4 meters, which I determined semi-graphically, plugged in the numbers for the value, and I get the maximum. Now the next part is I still need to know what happens up between 4 and 6 feet. So I can just do the same thing, only now go between 6 and 0, and I get m6 is equal to 120 kilonewtons. So if I go back to my diagram, what I have is the moment diagram goes from 0 to 160 parabolically, back down to 120 parabolically, but then at 6 feet the line becomes linear because shear is no longer a function, or it's a constant function. It has a constant value of negative 40, so I go from 120 to 0, and I can prove that out with the math as well. But it's all built into both the graphs and the math. So the most important thing that I wanted you to see here is that for that end spot, because v is constant, this equation is linear in x from 6 to 9. All right, so that solves the problem. So now you have both a graphical method and an analytical method. And you can see they're not entirely separate, but they both will accomplish the same goal, just some are suited more to one type of problem than the other. So I'll post a couple of homework problems, and this is it for Chapter 5. So we'll see you next week for beginning Chapter 6.